In next problem, you can observe there is energy level diagram for hydrogen-like atom. You can observe for the ground state, that is n equal to 1, energy is 54.4 with a negative sign and unit is electron volt, and n equal to 2, it is minus 13.6 and so on. In the first part of the question, it is asked find the value of Z, that is the atomic number. Second question, it is asked if initially atom is at ground state, then A question determine the excitation potential, and in the B part of the question determine the ionization potential. And third question, it is asked can it has absorbed the photon of 32 electron volt, and in the fourth question it is asked can it has absorbed photon of 54 electron volt. And the fifth part of the question, it is asked calculate the radius of the first Bohr orbit, and sixth question it is asked find the kinetic energy and potential energy of an electron in first orbit. Okay, so let us move one by one. Let us make the energy level diagram and let us first analyze the first part of the question to calculate the atomic number Z. So this is the question. Okay, you can observe here n equal to 1, energy is minus 54.4. These are the energy level. These energy levels governed by the formula which is given by En equal to minus 13.6 Z square divided by n square electron volt, right? If we substitute the value of Z, that is the atomic number, and for value n equal to 1, 2, 3, 4 and so on, we get the value of En, and we know these values are value of En. Okay, but here energy level diagrams are given and n is also given, and we need to find the value of Z. We can select here n equal to 1, this value minus 54.4. So here we can write n equal to 1, E1 equal to minus 54.4 electron volt. Okay, now we can substitute this value in this formula, and this n equal to 1, this is minus 54.4, that is equal to minus 13.6 Z square divided by 1 square. 1 square is nothing but n square. Okay, now let us solve for Z. Minus sign and minus sign will get cancelled, and here we can get the Z equal to under root 54.4 divided by 13.6, and this is a root 4, and root 4 is nothing, it is 2. That means the value of Z equal to 2, that is the atomic number is 2, that is helium. Okay, now let us move to the next part of the question. This is the next part. Question is if initially atom is at ground state, that means electron is at ground state, that is corresponding to n equal to 1. We need to find the first excitation potential. Let us analyze the first part, that is the A part of the question. We know the first excitation energy is the energy required to excite the electron from this orbit, that is n equal to 1 to n equal to 2. That means for this type of the transition, right? And this is the first excitation energy for n equal to 1, this is n equal to 1, and this is n equal to 2, right? And we are given the value of n equal to 1, and we are also given n equal to 2. That means we can find here the excitation energy, that's the first excitation energy, that is equal to delta E12, that is again equal to E2 minus E1. So let us write delta E12 equal to E2 minus E1, and that will be equal to minus 13.6 minus 54.4. Okay, let us substitute this value. So this is equal to, after solving, this will be equal to 40.8 electron volt. This is the energy required. And here we need to find the excitation potential, that is the first excitation potential. For calculating potential from energy given in electron volt, what we need to do, we should divide energy with E. If we divide this expression with E, this value will be equal to 40.8 volt. So excitation potential for this required value is equal to 40.8 volt. This is the A part. Now let us move to the B part, that is determine the ionization potential. Ionization potential is the energy required for eject the electron from ground state to n equal to infinite. That means to move the electron from ground state to out of the atom, that energy is the ionization energy. Okay, and you can say this energy, we know this energy is also the energy, that the magnitude of the energy at the ground state. So directly we can say that will be equal to 54.4 electron volt, because unit is here electron volt. So let us write this systematically. We know this ionization energy is the energy required to eject the electron from n equal to 1 to n equal to infinite. So we can write delta E 1 to infinite, that is equal to E infinite minus E1. And we know this E infinite is nothing but 0, and E1 equal to minus 54.4. So it is 0 minus 54.4, right? And this is numerically equal to energy at the ground state, that is a 54.4 electron volt. That means ionization potential, we need to calculate the ionization potential. This is the ionization energy. Here we need to do one thing, we need to divide this energy in electron volt with E. So ionization potential here will be equal to 54.4 volt. So this is the B part of the question. Now let us move to the C part of the question. No, that is the third part. There was only A and B, two parts. So let us move to the third part of the question. The question is, can it absorb a photon of energy 32 electron volt, right? Suppose electrons in this atom is at the ground state, it was given also, and it absorb 32 electron volt. That means the energy of the electron will become minus 54.4 plus 32. So let us absorb this energy to the atom at the ground state. So this is equal to 54 plus minus 54.4 plus 32. This is equal to 22.4 with negative sign, this electron volt. You know, if electron absorb this much of the energy, final energy will become minus 22.4 electron volt. But we can observe the next energy state is minus 13.6. That means if it absorb energy, the energy state should be minus 22.4. But there is nothing, no this type of the energy level. That means this atom cannot absorb 32 electron volt of energy, right? Because this energy level or this energy is between n equal to 1 to n equal to 2, and we know intermediate states are not possible in the atom, because electron can present only in the well defined orbits only. So this cannot absorb, that is 32 electron volt cannot be absorbed by the atom. Now move to the fourth part of the question, can it absorb a photon of 54 electron volt, right? That means if electron is at the ground state, that means it is having energy 54.4 minus 54.4 electron volt. After absorbing this much of energy, you know, energy of the electron will be positive, and we know at n equal to infinite energy is 0. That means after getting this much of the energy, this electron will escape from the atom. That means the remaining energy, that is 56 minus 54.4, that means the remaining energy will be available for electron as a kinetic energy. This energy absorption is possible. So this was the answer for the third part, and second part we have discussed. This answer is no, and fourth part answer is yes. By absorbing the photon of this energy, electron move out of the atom, and energy, because you know after this state energy is not quantized, that means remaining energy will available for the electron as a kinetic energy. Now let us move to the fifth part of the question. Calculate the radius of the first Bohr orbit. And we have the formula for the radius of the cell. We know that is radius of the nth cell equal to minus 5.3 n square divided by z, right, this much. This is the in angstrom. And if for hydrogen atom we want to calculate the first Bohr orbit, what we will do? We will substitute z equal to 1 and n equal to 1, and first Bohr orbit for the hydrogen atom is 0.53 angstrom. And here we calculated the value of z, that is equal to 2, and here we need to calculate the Bohr orbit, that means for n equal to 1. That means in the formula we should substitute n equal to 1 and z equal to 2. Right, and this value will be equal to R1 equal to 0.53 1 square divided by 2. This is equal to 0.265 angstrom, right, this much. This is the answer for the fifth part. Now for the sixth part, we need to calculate the kinetic energy and potential energy of an electron in the first orbit, right. Now we need to calculate the kinetic and potential energy for the first orbit. And we know the magnitude of the kinetic energy is equal to numerical value of total energy. And more appropriate, we can write kinetic energy equal to minus of E, that is minus of the total energy. We know this formula, and we also know the formula for the potential energy, that is potential energy equal to twice the total energy. So first of all, we can write kinetic energy equal to minus E and potential energy equal to twice of total energy, right. This potential is negative and total energy is also negative, and this is the negative value. That means this negative value multiplied by negative sign, this will be positive, that is kinetic energy is always positive. So here we can write E value for n equal to 1 is 54.4. So we can write here minus 54.4. If it is multiplied with the negative sign, this will be equal to 54.4 electron volt. So this is the kinetic energy for the first orbit, right. Now move to the second part of the question to calculate the potential energy. We know potential energy equal to twice the total energy, and total energy is minus 54.4. So it is 2 multiplied by minus 54.4, and this will be equal to minus 108.8 electron volt. So this is the potential energy. Okay. Now let us move to the next illustration. Next illustration again related with the energy level diagram. This is the energy levels for hypothetical 1 electron atom, right. This is a hydrogen like atom again, and this is the energy level diagram, but it is a hypothetical atom, right. The question is, first part of the question, it is asked, find the ionization potential of the atom, and in the second part of the question, find the excitation potential for state n equal to 3, and in the C part of the question, what is the minimum energy for the electron will have after interacting with the atom in the ground state if initial kinetic energy of the electron is, and first part this is 6 electron volt and second is 11 electron volt. Let us move to the first part of the question, that is the find the ionization potential of the atom. For calculating ionization potential, we need to find the ionization energy. And we know ionization energy is the energy required to eject the electron from the atom from ground state, that is from n equal to 1 to n equal to infinite, right. And here we know E for n equal to 1 is minus 15.6, and for n equal to infinite it is 0. So it is given, that is E1 equal to minus 15.6 electron volt, and E infinite, that is n equal to infinite, E value is 0 electron volt, right. And we know ionization energy equal to E infinite minus E1, that is the 0 minus 15.6 electron volt, and this numerical value is equal to 15.6 electron volt. That is magnitude of the energy at the ground state. We can directly say ionization energy is the energy, that the magnitude of the energy at the ground state. Now we can find the ionization potential. We should divide this quantity with the E. So this ionization potential is equal to 15.6 volt. So this is the A part, that the ionization potential we have calculated. Now let us move to the B part, that is the find the excitation potential for the state n equal to 3. Right, for n equal to 3, that is energy required, energy related with the n equal to 3 is minus 3.08 electron volt. And we know excitation energy. For calculating excitation potential, again we need to find the excitation energy. Excitation energy for state n equal to 3 is the energy required for this transition, that is from n equal to 1 to n equal to 3. For this transition, this is n equal to 1 to n equal to 3. So energy required should be equal to E3 minus E1. So let us first calculate the excitation energy, that is E3 minus E1. So excitation energy is E3 minus E1. Okay, and we know E3 equal to, we have calculated E3 equal to minus 3.08, and here this value is 15.6. So this is minus 3.08 and minus 15.6, and minus will be plus. So this value is equal to 15.6 minus 3.08, and this numerically it is equal to 12.52 electron volt. And for calculating the potential value, we should divide this quantity with E. So we can calculate excitation potential equal to E3 minus E1 divided by E, that is equal to 12.52 volt. So this is the B part of the question. Now let us move to the next part, that is the C part of the question. In C part of the question, it is asked what is the minimum energy that the electron will have after interacting with this atom in the ground state if the initial kinetic energy of the electron is 6 electron volt and second 11 electron volt, right? Let us first understand when an atom receives the energy for the excitation process. An atom can receive energy in the form of radiation, number 1, number 2 from collision, number 3 from heating. Only 3 processes can excite the electron in the atom, right? And if electron, outer electron, you can say external electron, is interacting with the atom, this electron will interact with the atom only if when it has energy equal to or greater than the energy required for the excitation of the energy for the second cell. That is, if electron is having energy greater than this energy, that is energy required for transition from n equal to 1 to n equal to 2, then only this atom, this hypothetical atom, will interact with the electron. That means, first of all, let us calculate the excitation energy for n equal to 2 state. That means that will be equal to E2 minus E1, delta E equal to E2 minus E1, and E2 equal to minus 5.3 electron volt and E1 equal to minus 15.6 electron volt. That is minus 5.3 minus 15.6 electron volt, that will be equal to 10.3 electron volt, right? That means if any radiation or atom, you can say any radiation or external electron have energy of this value or greater than this value, then only interaction is possible. And here you can observe this electron is having initial energy equal to 6 electron volt, which is less than the energy for excitation for n equal to 1 to n equal to 2. That means this energy, that is excitation energy for the second cell, is more than 6 electron volt. That means electron having the kinetic energy that is equal to 6 electron volt is not going to interact with the atom. That means the energy of the electron will remain same as previous, because it is not going to interact with the atom. Okay. Now move to the second part of the question. In second part of the question, energy is 11 electron volt, and we have calculated energy for the excitation energy for the second cell is 10.3 electron volt, and we have 11 electron volt. That means this electron can interact with the atom, right? Because energy having this much value, that is 11 electron volt. That means this electron is going to interact with the atom, and what will happen? This much of the energy, that is 10.3 electron volt energy, will utilize for this transition, and remaining part of the energy, that is 11 electron volt minus 10.3 electron volt, that is equal to 0.7 electron volt energy, will remain as a kinetic energy of the electron, right? That means energy of the electron after interaction will be 11 minus 10.3, that is equal to 0.7 electron volt. So we can say the energy after interaction, that is the kinetic energy after interaction, should be equal to 0.7 electron volt. Okay.